Let's keep going. When combining resistors in series, the resistances are simply added up as if they were one larger resistor. This is part of a larger effort to combine resistors. When we are looking at our circuits, and for this class at least, all we're going to have to worry about are looking at circuits with resistors in there. Different types of potential differences thrown in there, but for the most part, we're only looking at resistors. So let's say we have a circuit with 10 different resistors. And all of them are in series. We need to combine all of those resistors because as you add more and more resistors in series, right, think about the straws, then you are increasing the total amount of resistance for the entire circuit. So basically all that means is your total resistance in series is the adding of R1 plus R2 plus R3 and so on and so forth. So as you can see here, we started out with two resistors, R1 and R2. If we add them together, we get essentially one resistor. And that's what we're going to do as we're solving problems with circuits. When we're combining resistors in parallel, I have the three short straws, right? When combining resistors in parallel, the overall resistance decreases to produce a smaller equivalent resistance. And this is given by the formula, the inverse of the R total equals the inverse of R1 plus the inverse of R2, and so on and so forth. So if we have two resistors or three resistors in parallel, I know it's parallel because of that junction. So if we have three resistors in parallel, then we know the total resistance is going to decrease. So I think about it like you have a resistor here, resistor here, resistor here. Collapse those resistors. Crunch all of those down. So flatten all those resistors into just one resistor. And that one resistor is actually smaller than each of the individual parts. So this total resistance here is smaller than each of these. Another way to rewrite the formula, this is how it's given to you in your data booklet. The way that I prefer to write it is like this, where it's the inverse of R1 plus the inverse of R2, typo, in parentheses, and then take the inverse of that. And that's just so you don't forget to take that inverse. I find that students normally will do the inverse of R1 plus the inverse of R2 and think that that's it. They hit enter on their calculator and that's it. Speaking of calculators, your calculator has this to the negative 1 power button on there. So make sure you find that and use that. So it's going to cut down on your keystrokes on the calculator. So inverse of R1 plus the inverse of R2. And not take the inverse of that last answer. So think about it like this. Don't forget to take that last inverse. And you're probably going to forget to take that last inverse. Hopefully not, though. Okay, so let's say we have this situation where we have 4, 6 in parallel. And we have this situation, 4, 6, and 8 in series. Go ahead and combine those resistors. Pause it, try it out. Here we go. The total resistance here, because they're in parallel, because there's a junction, we're going to add the inverse of this, the inverse of this, and take the inverse of that again to get 2.4 ohms. Over here, it's a lot simpler. We love series. 6 plus 4 plus 8 is 18. Boom. There we are on your data booklet. Your total resistance. Series first, parallel next. More circuits. Which example has the least resistance? Assume every resistor is the same. Well, remember, the more we add in parallel, the smaller it becomes. So it's going to be this one. Equivalent resistance. All right, so we know this one is 1. We know this one is 3, so we'll go ahead and bring those down. To figure out this, we're going to collapse it, take the inverse of R1 plus the inverse of R2, and take the inverse of that answer to get 2 ohms. So 2 ohms goes there. Now, because I redrew this circuit, which is an important step, whenever you're combining resistors in series or parallel, or in series and parallel, I always recommend redraw the circuit as you move along, just to keep your thoughts in order. It's also going to help when you have to go backwards and try to figure out where is the lowest current or something like that, which we'll get to. All right, so the equivalent resistance here. Now we have the 1 ohm, the 2 ohm combined, and then the 3 ohm here. Now we have 3 resistors in series. 3 plus 3 is 6. So we have 6 ohms. Go ahead, pause, try this one. Give me the total equivalent resistance of this circuit. Here we go. I have these two in series, which are in parallel with these two. So I'm going to combine the series first, because I like those series. So 7 plus 2 here, 10 plus 8 here. All right, now I can see I have 2 resistors in parallel with each other. How do we add them up in parallel? Inverse of R1 plus inverse of R2, and inverse again, 6 ohms. Ohm's law. Here's are the big 3. If you know 2 of the 3 electrical properties, V, I, or R, as long as temperature is constant, we can use Ohm's law. R equals V over I. Kirchhoff's voltage loop. The sum of your potential difference equals 0 for a loop. Draw a loop. The voltage provided must equal the voltage dissipated. Useful if you have parallel branches to solve for. Kirchhoff's current law, the junction, current going into the junction has to equal the current going out of the junction. If this splits into parallel branches, the total should still add up. All right, so calculating series circuits. This chart here, this VIR chart, is done for each of the resistors. So for each of the resistors, we're going to be able to calculate the potential difference across each resistor, the current going through each resistor, and the resistor given to us, which is just given to us, so that's easy. All right, so we know the total equivalent resistance for this is going to be 6 ohms. So we can go ahead and, and we know the current is the same all the way throughout because we're in series.